Hi everyone, Professor Gonzalez here. In this lecture, I'm going to walk through some more steps in feature engineering, focusing on how we deal with missing values, how we encode categorical data, and how we encode text. In the process, I'll actually walk through doing some feature engineering on trying to predict the fuel efficiency of vehicles. The data for today's lecture is a classic data set that we can actually obtain directly from Seaborn. It's often used to teach regression or to study different statistical methods. I'm using it here because it's pretty easy to work with. It has both text, quantitative continuous fields, and categorical fields. The response variable in this data set is miles per gallon, the fuel efficiency of a vehicle. And the covariates that we're going to be using to predict that response variable are the cylinders, displacement, horsepower, weight, acceleration, model year, origin, and name. If we look at it here, the cylinders, displacement, horsepower, weight, acceleration, and model year are all essentially quantitative continuous fields. And so we could directly use those in a linear model to predict miles per gallon. So we'll actually start there, and then we'll come back to thinking about how we code the origin and the name. This dataset has several quantitative continuous features that we can use to build our first model. However, many of these features might need additional transformations, or we might have missing values. So let's first take a look at those features and the kinds of transformations we might want to apply. So one of the first transformations you want to think about, which really builds on our earlier discussion in data cleaning, is what to do with missing values. So first we need to figure out where are the missing values in this data. To find missing values, we can use the pandas data frame function isNA to find the missing values in each row, and then we can use the .any operation to find if any of the values in a row are missing, and we can use that to slice a data frame and pull out the rows with missing values to understand what is missing in our data. So in this data set, there's only a few rows that are missing. I think roughly 6 rows. Here's what is missing. If we zoom in, we see that horsepower seems to be missing in all of these rows. So for whatever reason in this data set, the horsepower wasn't reported for these vehicles. Again, in the context of data cleaning, we might want to understand why. And as we actually approach the modeling problem, I'll show you a trick to maintain additional information about the absence of those fields, which actually might be useful in trying to make predictions in the future. So the first feature transformation we're going to build is going to take just these quantitative continuous columns, extract them from our data frame, and then also replace the missing values with the mean. This is a standard imputation procedure. When you have a missing value, put the mean in. One caveat, one change that we're going to make here is that rather than just taking the mean, we're also going to add an additional column, a new feature encoding that original value is missing. This can be useful because sometimes the absence of data is data itself. So for example, the absence of a latitude and longitude at a restaurant might imply that that restaurant is off the grid. So we want to maintain the information about the absence of data in our model so that we could use that potentially as a feature. Now, in settings where the absence of data should not be treated as a feature, you would not want to then also introduce an extra column encoding that absence of data. So this is our first feature function phi. It takes in as an argument a data frame, the entire data frame, and it's going to project out the columns that we want to keep. I'm going to make a copy of this data frame because we might want to apply transformations and I don't want to modify the original underlying data frame. One thing you should know is that in Python, values are passed by reference, which means that manipulating the input data frame could actually be manipulating the input data. And so we're here going to make a copy to prevent modification of the underlying data. In general, you want to avoid modifying the data in the process of building features. We'd actually like to create new columns to encode whatever transformations that we want to apply. So in the second line of this function, we add an additional column, horsepower missing, which encodes the rows in which the horsepower is missing in the underlying data. Finally, in this last line, we replace the missing values in this data frame with the mean for those corresponding columns. This fill-in-a function will actually replace missing values in any of the columns with the mean for each of those columns. So now that we've constructed our first feature function, we can now use that function to fit a linear model. All right, let's get started. So the first thing we need to do is create an instance of the linear regression model and then invoke the fit function passing our transformed features. Now that we've fit our linear model, we can now go and evaluate the performance of that model on our data. Throughout the process of feature engineering, we're going to end up building many different models. And so it'll be convenient to have a way to track each of those models, the feature functions that we used for each of those models, and then actually report the error, the quality of fit of each of those models in a way that we can easily visually understand. So I created the evaluate model function, which takes as an argument the name, the model, the feature transformation phi, as well as a dictionary models, which will be the thing that I'm going to continue to update as I build new models and feature functions. This function will then compute the error of that model on my data using the feature function that was provided, store all that information in a dictionary, and then renders a plot that'll make it easy to see how I'm improving my model. When I go to evaluate the model, I see that the root mean squared error is 3.41. So that's a number. We'll see how that number decreases throughout the process. So I've got my bar plot over here showing the current fit of my model, the error. I'm trying to make it smaller, as well as this plot of y versus y hat to see if there's any structure in how my estimator performs relative to the response variable y. So there is some structure. So I'm going to try to improve the model to get all these dots to live along this red line. So unfortunately, the feature transformation we just implemented actually has a bug. Can you spot it? Yeah, so the problem is the feature transformation we just implemented uses the mean of the data that's passed into it to impute to fill in the missing values. Now, why would this be a problem? Let me show you. Suppose I pass in just a few rows. So here, for example, I'm going to go back to my original data and just select a few of the rows for which the horsepower was missing. Now, if I then go and try to make a prediction by applying my feature function to these rows with just missing values, the feature function will not be able to impute the missing value because it has nothing to take the mean from. It's not able to get the mean from the original data as it doesn't have access to it. So we see that the invocation of the model actually fails. So now let's go try to fix this feature function. Here I've re-implemented the feature function by capturing the mean of the underlying data which I want to use when imputing the missing values. So you'll notice that the second argument to the feature function takes in the data mean as a default value. And so that'll actually capture the mean at the definition of this feature function so that it will then be used when I invoke it in the future. Now, using this updated feature function, if I then pass in my new values where I am again missing the horsepower for all of the rows, we'll actually be able to successfully make a prediction. Because missing values are so common, scikit-learn actually has a built-in transformation for imputing missing values with different imputation methods. The simple imputer is the simplest of these transformations, but you can check out scikit-learn for other imputation transformations. Let me first show you how the simple imputer works, and it's actually a good representation of the kinds of feature transformations that are actually built into scikit-learn. So like models, feature transformations also follow a common pattern. The feature transformation is created by first creating an instance of that feature transformation, then invoking the fit function on the data from which you want to learn the mean or record statistics you're going to then use when you see new data. And then you invoke transform on that fit feature transformation to apply that transformation to new data. So let me show you how to use a simple imputer on this data set. So we first create an instance of the simple imputer. We then fit the simple imputer to our data. Notice here that I specified two of the columns that I want to impute missing values for. I could have just specified horsepower, but I also included weight just to expand the example. Now, when I invoke the transformation function, it's going to actually impute the missing values. Here, row 32 in my original data set actually contained a missing value, and now it's imputed that using the transformation step. Now we can use this simple imputer in original phi transformation by fitting it to just the horsepower column and then using it within inside the function body. Next, we're going to use domain knowledge to transform our continuous features to actually improve the accuracy of our model. Often during the process of feature engineering, we can use domain knowledge to create new feature functions that better reflect the phenomena we're trying to model. So for example, if we're trying to predict miles per gallon and we have information about the displacement of an engine as well as the number of cylinders, we could use knowledge about how an engine works to try to build a more informative feature. So in this animated GIF, you can see the internal combustion engine running, and you'll notice that only one cylinder is firing at a time. Now, the displacement is actually the volume of all the cylinders combined, but really what determines the amount of detonated fuel at each step or each firing of the engine is really the volume of the single cylinder that's firing. Now we can compute that volume by taking the ratio of the total displacement of the engine and the number of cylinders in that engine. So let's define a feature transformation that uses this insight to create a new informative feature. Here I've defined the phi with displacement feature transformation. It takes in a data frame as before. It's going to invoke our previous continuous feature transformation, and then it's going to extend that featureization with a new feature encoding the displacement per cylinder. We can now look at the output of this feature function, and we see that we've added an additional column here, displacement divided by cylinders, and this feature will hopefully be more informative of the fuel efficiency of the engine. To find out how much more informative, let's fit a new model with this new feature transformation. So you'll notice here in this updated plot, we actually have two columns here, one for our original continuous feature transformation, and a new column, which is lower, we've reduced the error, progress, for our continuous feature transformation, plus our new column that we created using domain knowledge, which is the displacement divided by the number of cylinders. So using that additional information, we're actually able to improve the accuracy of our model. You'll also notice here that the data is starting to fall closer along this y equals y hat line. So we're making progress, and now we want to return back to our original data and try to encode the columns that were categorical or text to see if we can further improve the accuracy of our model. A key step in feature engineering is encoding data that doesn't actually have continuous representations. And one of the common examples of that is categorical data. In this data set, we have an origin column, which takes on 3 distinct values. So you'll notice the origin column takes on 3 distinct values, US, Japan, and Europe, indicating where the vehicle came from. We might believe that where the vehicle came from might be indicative of its fuel efficiency. Perhaps cars made in the United States are more or less efficient than cars made in Japan. How do we encode this kind of data in our linear models? A naive solution might be to assign a number to each of these different categories. So let's say the United States is 1, Japan is 2, and Europe is 3. So unfortunately, that coding scheme is imposing an ordering and a magnitude to each of those different categories. And that might not be what we want. That's sort of implying that the US is lower than Japan, which is lower than Europe. And so a feature here, a coefficient of our linear model in this on this new encoding would mean that you could be more US or more European, and Japan is somewhere in between. That's not what we want at all. These are 3 distinct categories. This is nominal data, and so we want a different coding scheme for this kind of data. So the standard encoding scheme used for this kind of nominal data is one-hot encoding or dummy encoding. So I want to walk through how that works and how you can use it to encode this column. A one-hot encoding or dummy encoding takes a categorical column and constructs multiple columns corresponding to the distinct values that original column could take. So in this example here, suppose my column is state, and this is one of the 50 states in the United States that is stored in that column. So for each row, there is a corresponding state like New York, Washington, and California. Then I would construct a encoding where I create a new column for each possible state. And then for each row, I put a 1 in just the column that corresponds to that original categorical variable. So if the state was New York in row 1, then we would put a 1 under the New York column and a 0 everywhere else. So it's a sparse encoding of the category New York in this now 50 separate columns. The term one-hot encoding actually comes from digital circuits, which would use a single hot wire to encode one of k different categories. Now let me show you how to construct a dummy encoding or one-hot encoding using pandas. Pandas has a built-in function called getDummies, which takes a data frame and constructs a dummy encoding for the categorical columns. So here we'll apply the getDummies function to the origin column in our data frame. Notice how when we invoke this function, we've actually created 3 separate columns from our data frame with a single column, where each of those columns is either 0, 1, depending on the value of the original categorical variable. So the first row in this data frame, the row here, has 0 for origin Europe, 0 for origin Japan, and 1 for origin US, indicating that that vehicle came from the United States. So now we can use this transformation to create a new feature function which computes the dummy encoding of our origin column. Here the fire_with_origin function applies our continuous transformation as well as our displacement divided by cylinders transformation, and now we'll extend it by adding an additional set of 3 columns encoding the column corresponding to the origin of that vehicle. So we can now look at what this feature transformation looks like, and you see that it has all the original columns plus our displacement divided by cylinder column and our 3 new columns corresponding to the dummy encoding or one-hot encoding of the original origin column. We can now evaluate our new feature function and see if it reduces the error in our predictions. So you'll notice now we have 3 columns, the first corresponding to our original just continuous features, the second corresponding to our continuous features plus displacement, and our third corresponding to continuous features plus displacement plus the origin. And you see that this had a small impact in accuracy, so we reduced the error by a small amount. It was originally 3.02 and it is now 3.006. So we were able to reduce the error a little bit. So perhaps the origin didn't provide that much additional information in estimating the fuel efficiency of our vehicle. So now as before with our imputation of missing values, we've implemented a feature function that would actually not be robust. Can you see what we did wrong? The feature function we just implemented constructed the dummy columns based on the data that it had seen. So if we were passing a single row to that feature function, it wouldn't know how many columns to create in its dummy encoding. So let's actually test that here. I'm passing a single row from our original data set into our model to make a prediction. And by invoking this fire_with_origin feature function, it's going to fail to construct the right number of columns. And to see exactly what happened, if I just invoke the feature function on a single row in my data frame, I get an output which only has origin USA as the single encoding of that categorical variable, because we didn't know that it could take on Europe or Japan as other possible values. So as before, to fix this, we can actually turn to scikit-learn and the built-in feature transformations to use the built-in one-hot encoder in scikit-learn to first fit to the right number of categories and then apply that transformation to both original data and any new data we might encounter. So let me show you how to use the scikit-learn one-hot encoder to transform the origin column in our data frame. Just as with model prediction, the first step is to create an instance of the transformation. So here we create an instance of the scikit-learn one-hot encoder. Then we fit that transformation to our data, and this is going to determine the number of categories that that column can take. And now we can transform our data frame using this fit encoder. You'll notice that the output of the one-hot encoder is actually a sparse vector, a sparse matrix, and this is because most of the columns are going to be 0 in the one-hot encoding. Now in practice, we wouldn't want to encode this to a dense representation if there were many different columns, but since there's only 3 here, we can take a look at what the dense representation would be. And as you see, it's all zeros except for the column corresponding, in this case, the United States, which would be 1. As you can see here, for the first 5 rows of our data frame in which the origin is the United States, only the US column is set to 1 and all the other columns are set to 0. The one-hot encoder also allows us to extract the underlying feature names. So here the 3 columns correspond to Europe, Japan, and the United States. So we can re-implement our feature transformation, which applies a one-hot encoding to the origin column using the one-hot encoder from the scikit-learn package. Now when we invoke the phi transformation on our single row data frame, we'll actually get the correct values. Now when we invoke the feature transformation, which is encoding the origin using a one-hot encoder, and we only pass in the first 5 rows of our data frame for which all the origins are United States, the encoding still has the other 2 columns corresponding to Europe and Japan. The remaining column in our data set is the name. This is a text field with the name of the vehicle, and every row is going to be distinct. And so if we were to use a one-hot encoding or a dummy encoding of this, we'd actually just get a column for every single row, and that's not what we want. So if we look at the name field, we notice that there are multiple words in each of the name, and some of the words like the brand, Plymouth, or Mustang might be indicative of the fuel efficiency of that vehicle. So we need a mechanism to encode each of these words separately that captures some of the ideas of this categorical encoding, but can be applied to whole fragments of text. So now I want to show you how we can generalize the one-hot encoding idea we saw earlier to entire sentences of text. And so now what I want to talk about is the 2 kinds of encodings that we can use to encode text, some of their strengths and some of their weaknesses. Now, one of the big challenges in coding full blocks of text is that it's actually going to be effectively a little lossy. When we did a one-hot encoding of the origin, we were able to preserve the complete information, so we could go from the dummy encoding back to the original origin column. If we were to do the same thing where we set multiple columns to 1 corresponding to the words in a sentence, we lose information about the ordering of those words. So we'll also talk about n-gram encodings, which tries to preserve some of that information by, instead of encoding each column or each word as a separate column, we look at pairs or triples of words as distinct columns. And so we can start to see at least local information about the ordering of words. Now in this class, I'm going to focus on pretty standard techniques for encoding text, but the state of the art today has actually come a long way. So if you're interested in learning more about vector representations of text, check out the link I put in the notebook to a post describing the BERT model, which is now one of the more standard approaches for representing large fragments of text in a vector representation. So let's start the bag of words encoding. The bag of words encoding is probably one of the most widely used encodings for text. It is, as I described earlier, a pretty natural generalization of the one-hot encoder. So I create a separate column for every possible word in the language. This means I have to know all the possible words I might see in advance. If I were to take English, I might take all the words in the English dictionary and create a separate column for each word. And then to encode a sentence like learning about machine learning is fun, I then go to each of the columns corresponding to the words, like the word fun, which occurs once, and I set the count or the entry in that column to the count of that word. So fun occurs once in the sentence, whereas learning occurs twice in a sentence, so I set the count for learning to 2. You'll notice that all the other words are set to 0. So again, this is going to be a very sparse encoding of a sentence as a very high dimensional vector. There are some caveats in using the bag of words model. First, we often will drop stop words. These are words like is, the, that don't really encode a lot of information, and so we don't really want to keep those as columns. Second, the bag of words encoding loses information about the ordering of words. Now, in many cases, like this sentence here, learning about machine learning is fun, if I tell you that there's a sentence which contains fun, learning, and machine, you might have a general gist about what that sentence is describing, but specific details or nuances could be lost. So for example, if I were to say, not learning about machine learning is fun, that has the same encoding as learning about machine learning is not fun, but it means something very different. Third, it is common to drop things like capitalization or punctuation when constructing a bag of words encoding. But in the time of emojis, we might actually want to preserve some kinds of punctuation which could actually encode really important information. Perhaps if you're writing a review, an emoji might really capture the sentiment of that review. However, to encode emojis, we'd have to actually introduce new words in our vocabulary. We'd have to extend the dictionary to treat a smiley face as a distinct word. Finally, as you might have started to notice, the bag of words encoding is going to be very sparse, so we might introduce tens of thousands of new columns, for which only a few of the columns are actually going to be non-zero. This creates challenges both in how we store the bag of words encoding, but also how we fit models. Because as you already learned, if we have more columns than we have rows, then the matrix inversion in our normal equations will no longer be well defined. And so in coming lectures, we'll talk about how we deal with that. When I was a graduate student, I actually participated in some guerrilla art. We got a new building and it really needed some art to liven it up. And so we created a bag of words sculpture where we took a Nigerian email, a spam email, because bag of words models are actually widely used in spam classifiers. And so we took that email and we extracted all the words and we cut them up and put them in a bag, losing all the ordering information, much like we just discussed earlier. And so we, in a sense, constructed a bag of word encoding. And someone could walk up to the bag, it was clear, and look in and go, I can try to guess what the text of that original email was describing. And you'll notice on the floor, we have all the stop words. We didn't include those in our bag of words. So words like the, to, this are on the floor. I will also add we had a broom attached to this exhibit, but the janitors took our broom thinking it was not part of the exhibit. So now let me show you how to use scikit-learn to implement a bag of words transformation. So first, let me show you how to do this on a simple block of text, and then we'll apply it to the name column. So here I have a snippet of text from a famous poem, and I've split it into separate lines. And for each line, we're going to construct a bag of word encoding of that text on that line. Just with all the other feature transformations, the first step is to create an instance of the bag of word encoder. In this case, it's actually called the count vectorizer in scikit-learn. So we create an instance of the count vectorizer, and then we're going to fit that count vectorizer to our text. We need to fit our count vectorizer to the text because we need to know the vocabulary, the space of words that we could see in our text. This is just like with the one-hot encoder where we needed to see each of the distinct categories that we could have to encode. So once we fit our count vectorizer to the text, we can now use it to transform that text into a bag of words encoding. And this is done by invoking the transform function. We can now see the words in our vocabulary by invoking the get feature names, just like with the one-hot encoder. And so here we see that words desire, end, favor, hold are in our vocabulary. You'll notice that when I constructed this count vectorizer, I set stop words to English. So it's going to automatically drop common English stop words. So now we can apply the count vectorizer to each line of our poem, transforming the text into a vector encoding. Notice that I've converted that sparse vector encoding into a dense vector encoding so we can visualize it easily here. If there were many more words in our language, that would be hard to see on the screen, so we'd want to keep it in the sparse representation. Now, one of the limitations of the bag of words encoding, or using the count vectorizer, is that it loses information about word ordering. We can partially account for that lost information by using an n-gram encoding. An n-gram encoding is actually a pretty simple extension of the bag of words encoding, where instead of encoding the counts of single words, we encode the counts of pairs, triples, and so on of words, so clusters of words. So in this picture here, we have the book was well written, and we can construct an n-gram encoding where n equals 2 by taking the book and treating that essentially as a new word. Book was is another word, was well another word, and well written another word. So we cluster pairs of words, and then we're going to keep track of the counts of these pairs. What that means is that our feature encoding will create columns corresponding to all possible pairs of words in our vocabulary. So this is going to be a very high dimensional vector representation of these counts. So this encoding has the strength that it does preserve word ordering, but it also puts us in a much higher dimensional space. And that's going to present more computational challenges and also more modeling challenges, because again, as we add more and more columns, we're going to run into rank deficiency issues. We're not going to be able to invert our normal equations. As you will see in upcoming lectures, this will also present significant challenges as we start to think about generalization. To address the computational challenges, there are techniques that exploit hashing and other sketching strategies to essentially reduce the vector space down to a smaller, in fact, fixed vector space, and then hash each of the pairs of words or triples of words into that space. We then allow for collisions, but in practice, that actually doesn't really affect the accuracy of the underlying n-gram encoding. To implement an n-gram encoding, we actually use the same count vectorizer that we used when constructing the bag of words encoding, but we pass an additional argument when we create an instance of that count vectorizer. So here, we're going to construct a count vectorizer where n-gram range is set from 1 to 2. This encodes a bigram, or this represents a bigram encoder. The first value saying 1 means that we're going to consider unigrams, which is the original bag of words encoding, as well as the bigrams. So we're going to look at every single and every pair of words in the set of columns that we're going to construct in this bigram encoder. So if I then fit the bigram encoder to our Frost snippet of text, it will look at all distinct single words, as well as all possible pairs of words, and it will extend our feature representation to consider all of those values that we saw in that text, which means if we see new text with new pairs of words, we won't be able to encode those in our representation. However, when the count vectorizer encounters new text that is either single words or pairs of words it hasn't seen before when applying the transformation, it's going to drop those words or pairs of words, essentially leaving the entire row all 0. So we fit an instance of the count vectorizer, and now we can look at the feature names that are constructed from this. So here we see all the single words as well as pairs of words as distinct features. So these are now distinct columns that we can encode in our feature space. And I can also apply this count vectorizer with, again, unigrams and bigrams. And this is the counts of all of those unigrams and bigrams for each line of text in the Frost passage. All right, so I want to wrap up by applying the count vectorizer. I'm going to look at the bag of words encoding of the name field in our data set. So we're going to create an instance of the count vectorizer. I'm going to fit it to the name column, and then I'm going to append these new set of features to the features that we defined earlier. To give you an idea of what this new feature transformation looks like, I'll go ahead and apply this full set of features to our data. And you see here we have now 311 columns. I've taken just the head, so 5 rows, but 311 columns corresponding to our original set of continuous features, our feature transformation of displacement divided by cylinders, as well as our one-hot encoding of the origin, and then all of these separate columns corresponding to the distinct words in the name column. Now at this point you might be wondering, if I use all this additional information, can I improve the accuracy of my model? And so we will evaluate this new feature transformation using our evaluate model function. So when we combine all of these feature transformations, we can actually significantly reduce the error in our predictions. So we had started out with a root mean squared error of around 3.41. When we just included this additional column of displacement divided by the number of cylinders, we were able to bring the error down to 3.02. And then when we added just the origin, we were able to slightly reduce the error to 3.006. But when we introduced the name in this one-hot, or the bag of words encoding of the name, we were able to significantly reduce the error down to 1.3566, so on. So that was a big step forward. We really improved our model, and hopefully some of you are starting to wonder, but was it worth it? And so in the fireside chat, I talked a little bit about some of the dangers in making our model increasingly complicated. Perhaps these kinds of feature extensions, like the name of the vehicle, encoding things like the manufacturer, might actually be useful information, but taking the full name could have added perhaps too many columns. As we'll see in the coming lectures, the addition of too many columns can have significant implications on the ability of this model to generalize to new data. So that concludes the video for this notebook. I hope you like this new format. Please let us know what you think on Piazza. Happy feature engineering.